Okay, welcome guys. So this is the first class for PyTorch, deep learning in PyTorch. So the basic assumption of this class is that the audience already knows Python. Some of machine learning you already know, and a little bit of deep learning also you know. You have an idea that how it works. So that is the basic understanding of this or assumption of this class. And so we will be mainly focusing on developing DL models using PyTorch. So that has been a challenge. And I personally know all of you, so I know where you stand. And although we have a proper understanding of what is deep learning and how things work, and we might have also written some models by ourselves, but that is mostly copy paste work by somebody else GitHub code. So the objective here is to reach to a position where we can read a research paper and code that research paper from scratch by ourselves. So that is the goal of this total tutorial. uh, After the end of this tutorial, we should be able to, each and every one of us, including me, should be able to read a research paper, understand the math, code that math in PyTorch, and build models from scratch, not taking from anybody else's code or GitHub repository, right? So that is the kind of independence in I am seeking for and I am looking for. So I hope we all will reach there, and that will be really good if we can. And that is the and that is the most uh, big demand of machine learning or deep learning in the market now. So that is the goal. Okay. So saying that, first class, one or two classes will be little repetitive for you guys. Might seem little repetitive. That it is the same thing, but just a minute. Okay, so we will. So what I will suggest you guys is that have a note and pen copy ready with you, and so that we have proper notes of the class. And after the class is over, the recording will be available in YouTube. So you can go through that offline and create your own notes. Okay. Notes making is very important because now you will understand everything, but there is so much content that you will forget. It happens to me also. So that is my policy, that take the notes every time, whenever you get time, revise the notes. So that is the way you get remain up to date. Okay, so that is the policy that we will also apply here while doing. One more thing, I am not going to uh, train means do any coding on Google Colab or Jupyter Notebook. Okay, which is the common way in which it is done in tutorials. So I don't personally encourage that way of doing, because ultimately when you will be working in a project or any company, you won't be doing it in Google Colab or Jupyter Notebook. It is basically for just experimental purpose. So we will be doing real work on either Visual Studio or PyCharm kind of IDEs. So we'll have to have proper knowledge of the backbone or the frameworks that are needed for this development. Okay, so because when you go to Google Colab, by default there are so many libraries already installed in that you don't understand what is required for this type of development, right? So that is one of the main important reasons that I will be developing. I will be developing all my tutorials in PyCharm. Okay, so that is given for that. Okay. Now, one more thing is that I don't expect all of you to have a GPU server with you guys, okay? But mm, but luckily I have a GPU server with me, and the machine on which I am teaching you has a GPU connected with it. So what is the benefit is that I can show you how we can make utilization of the GPU using PyTorch and develop codes either in CPU or GPU or a mix or hybrid model, or what is the best way of doing it. Those things I can explain you. Although you cannot practice it at your home, uh, but you can always see from here that how the things work, so you will have an idea. Okay. Okay. Saying this, we will start the course. Uh, so, hmm, just a minute. Okay. So we will come to I am starting. I'll share my screen. You guys tell me when you see that. Can you guys see my screen?
Yes.
Okay, good. So as I said, first one or two classes will be a little bit repetitive, but things you might already know. But there will be definitely many things that you can learn from here. Okay. So let's start with a simple linear regression. Okay, I'm assuming that you already know some machine learning already, right? So according to that, I am talking about it. So who can say the basic equation of a linear regression with a single feature?
Y is equal to mx plus c.
Y is equal to mx plus c. Okay, here what is x, what is m, what is c, and what is y?
Y is the line which we are predicting the best fit line, and m is the slope, x is the feature, and c is the constant.
Okay. So here, as you said, x is the feature. Okay, x is the feature and y is the predicted feature. Okay, m and c are learnable parameters. Okay, although we call it by a special name, slope and intercept, but in generic terms of machine learning, they are called learnable parameters. So basically, these are the parameters that we will learn. Okay, by the help of the data points that we have in x and y. So that is the target. We have to learn m and c, which are the learnable parameters. So the general equation will be little modified here. Okay, so the general equation will be y is equal to b plus wx plus epsilon. Okay, so this equation is very similar to this equation, but I have added an extra term, that is epsilon. What is that? I will tell you. So now the physical significance of this equation is that if x is 0, okay, and epsilon is 0, then y is equal to b. So that means b is the base value. That means y can never be less than b, right? So b is the minimum value that y will always be having. Okay, so that is this is the base value, and epsilon is the error added to the end to compensate the error, because we always might not have been calculating in a perfect manner. So epsilon is the error found in that calculation. Okay, that's why we have added epsilon. It can be a distribution from some -1 to +1, a uniform distribution or a Gaussian distribution, which can go in here and it can give us a very nice linear regression graph. Okay, so this is our, now this is our parent equation. We have to work on this equation. Okay, now let's move forward, and as I said, we have to learn about two parameters. What are those two parameters? B and W, right? B and W are the two parameters that we are going to learn. Okay. Now, let's generate some data for the sake of our problem. Let's generate some data for the sake of our problem. I will start with the empty project, new project. This is the also steps that you have to follow. Okay. So oh, you guys cannot see my PyCharm screen, right?
No, so we cannot see.
Okay, okay. One minute. Can you see now?
Yes, yes, we can.
Yes. We create a folder. Here we create a folder. Mm. So inside PyTorch class 1. Okay. Okay. The project is starting up. Yeah. Is it visible now?
Yes, it is visible.
Yeah. Okay. So now this is a blank project with just a virtual environment in it. Okay. So now we have to install PyTorch in this one. Okay. So for that, what we have to do for installing PyTorch, the command is let's not go to PyTorch now. Okay, no, we are still into linear regression. Okay, so let me do this thing. So create a Python file. Test1. Okay, so we create. So now, why I am taking a B value? I'll tell you that later. Let me first write down the code here. Okay.
Basically, like epsilon can be of any range, right? Since it is an error. So why
Yes,
are
yes.
we range?
I'll tell you. I'll tell you.
Okay.
So here, what I am doing, here I am generating data for my. I'm generating data for my linear regression. Okay. So synthetic data. So this data is my own data. Okay. So what I have done, can I generate my synthetic data without a B and W? I cannot, right? Because the equation y is equal to mx, y is equal to b plus wx plus epsilon has the two variables b and w. So I have to initialize the b and w to a certain value, okay, and then I have to start generating data for that. But that b and w may not be the best one. As we all know, in linear regression, we gradually reach to a value of b and w, which is the best fit line. That is our theoretically we know that, but we have to start from somewhere, right? I cannot keep b and w as unknown and get the value of y, right? So that's why I will start with a value of b and w, that is 1 and 2. Now this b and w, whether it fits this x distribution properly or not, I don't know. We will see that. We will see that how if it is fitting. If it is not fitting, then what can I do to fit it properly? We will see that. Okay. Now, what is n? N is I want to generate 100 data points. Okay. For my linear regression, I want to generate 100 data points. What is random seed? This is for reproducing our experiment. So if you set the seed to a particular number, then this random number generation will always generate the same numbers you do it. So our experiment can be reproduced in the same machine. Across the machine, it will not be the same. But in the same machine, it will be the always same. So it will help us compare apple to apples and oranges to oranges instead of two different distributions. Okay. NP numpy random.rand, what it does, it gives you a uniform distribution of n numbers. Here n is 100, so we get an uniform distribution of n numbers, which is x. So consider in the x coordinate, in the imagine there is a coordinate system, and in the x coordinate all these numbers are there. Okay. Now I have to calculate the y coordinate. Okay. And the formula for y coordinate is what? Y is equal to b into wx plus epsilon. Now I have to also initialize epsilon, because epsilon is also a distribution like x. But here what I have done here is I have multiplied a factor of 0.1 with the same. I am getting 100 random numbers, and I am multiplying a factor of 0.1 with it, and I'm telling that this is the epsilon. Why I am multiplying 0.1 factor with it? Because I'm keeping the error range at the maximum of 0.1. Okay. So if you see the definition of numpy's random random, what it says that it returns a sample from the standard normal deviation distribution. Okay. And it gives a parameter, the dimension of the array returned. Okay. So here it is the dimension of the array returned. What is the dimension? Okay. Let's run and see this one. What is the output coming here? Okay. If you see, X is a array of size 100, 1, that is n, 1, and epsilon is also an array of size 100, 1. Okay. Now you can see here that X max value is from -1 to +1, and epsilon's max value is 1/10th of that value. 1/10th of that value, because I am multiplying 0.1 with it. Now why I am multiplying 0.1 with it? Because the error is less, right? The error is always less than the original distribution. So if my original distribution is ranging from -1 to +1, then my error range will be always less than that, and not a little bit, but much less than that. So as a assumption, we have done it 0.1. Now you can tell that, can we not do it 0.01? Yes, we can do 0.01 also. If you want to keep the error much smaller, then you can keep it 0.01. Okay, but here 0.1 is good enough, because we are making the error 1/10th of the total standard random distribution of n. Okay, now with this value I am getting my y. Okay, so I am getting x, y. I am getting all the x, y values. Okay, y is here, x is here. So total, my data generation is done now. Data generation is done. How I am generating the data? Again, just explaining. I am randomly taking a value of b and w. I am randomly initializing 100 points of x. I'm randomly initializing 100 points of epsilon, and using all these values, I am generating the value of y. Okay, and this is a linear regression, because I am generating the value of y using this equation. Okay, and this equation signifies the linear regression. Okay, now coming to further. Okay, now we have to now you all know that we have to split our data into training and validation. We have to split our data into training and validation. So I'm assuming these things are already known, so I'm not going with it. So I'll just go ahead. Here it is. I'm getting a range of indexes from 1 to 100. Okay, and then I'm shuffling the indexes to make it more random. I'm getting the training indexes, which is 80% of total n, and I am getting the validation indexes, which is remaining percentage of n. Okay, and accordingly I am generating x and y training data, and I am generating x and y validation data. Now you see, I am doing all this here manually. Although we all know that in scikit-learn, sklearn, we have standard methods for doing this trend split. So question may come to your mind that why we are going through all this pain and splitting it in this way, which is completely manual. This is because of our clear understanding, because these things will be required when we move to PyTorch. It will make a lot of things clear when we move to PyTorch. Okay, so if I would have used directly the library, then a lot of things would have been obscured and we would not know. That's why I am doing it. So for 1 or 2 classes, just bear with me, and once our base is set up, we will go to PyTorch and then do our thing. Okay, so what we did now, we randomly initialized b and w. We randomly initialized x and epsilon. Using all these 4 values, we got the y value, and this is our data generated for linear regression. We created n 100 indexes, we shuffled those indexes and we created 80% in the indexes for training data and 20% in indexes for validation data. And we got our training and validation data from there. Okay, this is how much we did. Now, if we plot this data, you will see that it is a good linear regression data in this format. I am not showing you the plot because you can visualize it, right? It is a XY plane and it is a linear regression data. Or if you want to see, I can show you this. So you can see here. So this is our this is the training data and this is the validation data. Okay, and now who can say why this is not a straight line? I used y is equal to bx plus c, mx plus c equation, but why this is not a straight line?
Because of the randomness we created.
No, it is because of epsilon.
Yeah, error is that.
The epsilon adds the noise, and hence that we are not getting a straight away straight line. We are getting some lines in outliers also we are getting. That is because of the noise. Okay. Okay. So this is how we got the distribution. We have now training data and we have validation data. So we'll move forward. Okay. Now, I initialized just a minute. I'll, instead of going through that code, I'll go through this one to be quicker. Okay. Now, in our example, we used a random initialization of B and W, which is 1 and 2, right? So instead of 1 and 2, we could have gone for a random initialization in this format also. NP random 1, NP random 1. This will give randomly initialize B and W to some random values. Okay. And we can compute the model's prediction by this formula. Okay. After we have calculated, now with the this is the actual data, right? This is the linear regression data that we generated. Now for a random B and W, this is the linear regression line, which is very much away from the original distribution. And it is expected because we randomly initialized B and W, right? There was no guidance that we used in getting the value of B and W. We randomly just took some value of B and W, plotted a line. But what we can do is that we can check how bad is this line, right? How bad is this line? How we will do how bad is this line? By taking MSE, mean squared error loss. This one you all know. First is take the difference between every x value, like when x equal to 0.4, what is the value of y here? What is the value of y here? Subtract both of them and square it and add it with the other values. So that is the mean squared error loss. So who can say the difference between error and loss? So here is the definition. Error is the difference between the actual value and the predicted value computed for a single data point. Okay, whereas loss is, on the other hand, loss is for the aggregation of all data points. Okay, aggregation of all data points. So when you apply sigma, then it becomes loss. When you only look for a single data point, that is the error. Okay. Now these 3 points is very important to remember. Okay, batch, mini batch, stochastic gradient descent. Okay, now remember that our duty is to calculate the perfect B and W which fits with this distribution, right? That is our linear regressions goal, right? We started with a random B and W and we found that it is very much erroneous. But ultimately, we will rotate this line and we will reach here and it will be best fit. True, and we agree, all agree. But while we are doing this, while we are moving, rotating this line and bringing it here, how many data points are we using to calculate the loss? How many data points are we using to calculate the total loss, this aggregation? How many data points? If we are using all the data points at the same time, then it is called batch gradient descent. If we are only using a single point, single data point, then it is called stochastic gradient descent. And if we are using somewhere between 1 and n, then it is called a mini batch gradient descent. Okay, so these three things will come very often in our class, what we will study, right? Batch gradient descent, stochastic gradient descent, mini batch gradient descent. Okay, that means what? We all know this one. So MSc, this is MSc. You all know what is MSc, right? Y hat means the observed value minus the expected value whole square sigma by n. This is the mean squared error loss. Okay. So here, programmatically, you can get this value. So let us do this thing here. Just a minute. Let's do this. So this is true B and true W, right? True B and true W got us the original data. Okay, the true data, the true distribution. This is B and W. What is the difference between B and W and true B and true W? B and W is the B and W which we want to find that best fits with this true B and true W. Okay, so this is what our goal is to find. Okay, this is going to change, but this is not going to change. This is fixed. This one we use to generate our data. Okay, so B and W, we generated B and W. Now simply we get the value of y hat. Okay, so you get the value of y hat is equal to B plus W y hat is equal to B plus W into x trend. Okay, we'll calculate the error now. Error is equal to y hat minus y trend. Loss is equal to error whole square mean. Okay. And print the loss. Okay. So loss is 15 here. Now this is for one epoch, right? This particular thing happened for one epoch. That means I have a random, I started with just random B and W. With that random B and W, I generated some Y value. I calculated the error and I printed the loss. Now we all know what is gradient descent, right? Gradient descent means I have to calculate the values of B and W after every epoch, so that I can adjust this loss and make this B and W change so that the linear regression line is slowly going to be a best fit line for the original wide distribution, linear regression distribution that we had. That is extreme and wide trend, right? So our target is to find adjust these values of B and W based on the loss we get at every epoch. So that means what I can do, if I have number of epoch is equal to say 100, then I can say for epoch in range n epochs, I can do this, right? I can do this. So that means for every epoch I am calculating the loss, but I am missing something here. What am I missing? Who can say? What should be added? What line should I add here?
Every time updating B and W.
Yes, we have to update B and W, right? But how we will update? What is the formula?
You have to take the derivative.
Yes, we have to take the derivative. There comes the main gradient descent concept, which I will show you in picture now. Okay. Now let us talk about loss surface. Okay. Forget about this code. See it here. Okay. This is the loss surface. Okay. This is the loss surface. Now you see, this is B, this axis is B, and this axis is W, and this axis is the what? This axis is the loss height, total loss, right? The x-axis is B, y-axis is W, and z-axis is the loss. Okay, so for certain values of B and certain values of Y, we have certain value of loss. If I plot this loss graph with a continuous range of B and W, then I will get a graph something like this. Okay, I'll get a graph something like this. So purely we can see that the graph's minimum point is here, right? So B is somewhere, if B is somewhere little more than 1 and W is somewhere between 3 and 4, then I am getting the minimum loss, right? So my goal is to reach here as per gradient descent. Okay, I'm not explaining gradient descent in detail because I assume we all know it. Okay, so my goal is to reach here in the minimum loss I have to reach, which is for a range of B and W, I have to reach here, right? This is my minimum loss, but this is the entire range of W and B. I started with a random value of W and B. Okay, so this is contour plot. This is surface plot. This is contour plot. This contour plot means every line tells the height of the graph. Okay, this blue line tells that it is 3000 think like that. It is 3000 meters above sea level. This is 6000 meters above sea level. This is something. So this one is increasing in this side. This one is also increasing in this side. So this is the minimum. And I started somewhere here, random start. Right? If you remember, I started, B was NP rand was single value, W was NP rand a single value. So that random value started here. My job is to go from here to here. Right? My job is to go from here to here. How will I go? How will I go in code? Programmatically, how should I go? Okay, that is our that is the goal of our gradient descent. Now, one thing you may ask me that here only B and W are two learnable parameters. That's why it is easy to visualize and maybe calculate also the path. We can still mathematically calculate this path from here. Although it is not very easy, but we can still calculate the path from this random start point to the minimum point, right? But if I have, say, 10 learnable parameters in a equation, then I cannot even plot that graph. How will I reach the minima for 10 learnable parameters at the same time, right? So here we are visualizing that this is the path from random start point to minimum point in a 3-dimensional graph. We still don't know how to calculate this path, but at least we can visualize it. But when we go for a equation, instead of a linear equation, say a polynomial or a quadratic equation, where the number of learnable parameters is more than 2, then how do I visualize the path from the random start point to the minimal point? And how do I calculate that path? So anybody can say how to calculate that path? Divi, Dennis, you guys are completely quiet. Are there in the
नहीं पता सर actually.
Sorry, I didn't get you.
सर मतलब idea नहीं है कि how we will calculate the path.
Yes. So okay. So this is here we will come to a concept called cross sections. Okay, cross section. This is very important. Cross section means, imagine this is a 3-dimensional graph, right? If I make W constant, then I can think of a plane in where W is 2. So if I make W is equal to 2 constant. So there is a plane here, right? I don't know if you can imagine, but I will show you here. Here. Okay, so here is my 3-dimensional graph, right? This is the linear regressions. This is B, this is W, sorry, this is W, and this is loss. I wanted to reach here. From this point, I started randomly at this point, and I want to reach to this point. Okay. Now, I don't know how to reach to this point because I have so many parameters. Now here is only 2 parameters. That's why I can visualize it and I can think of some mathematical equations to reach there. But if it is 4 or 5 parameters, then how do I do that? So in that case, what we do is we make W constant. Out of 2 parameters, let us make 1 parameter constant. Suppose I make W at this point constant. So if W is constant here, then imagine this is a plane like this. Okay. So this plane's equation is what? W equals to say 2. W equals to 2 is the equation of this plane, right? For various values of B, W is always equal to 2. Okay. Now, if this equation is slicing this three-dimensional graph like a knife cuts a part of cheese, right? Imagine this red color is a knife and it is cutting this three-dimensional curve like a cheese. Then what I will get? I will get a cross section. I will get a cross section like this, right? If I cut it like this, I will get a cross section. Any doubt here? You are getting the point?
Yes.
Yes, sir. Yes, yes.
Yeah. So when you get a cross section, then what happens? That cross section is what? It is a two-dimensional graph only, right? If I slice a three-dimensional graph, what will be the dimension of the cross section? Two-dimensional. A single line, isn't it?
Yes.
So, and now this is to calculate how to reach from this red dot to this minimal point. It is very easy now. Now that's what it is telling here. See, keeping B as fixed to 0.52, this is the way W will change. Okay. And similarly, keeping the value W as fixed, this is the way B will change. So that means the rate of change of W, if W changes a little bit, loss changes little bit, because the slope is not that much. It is not very steep slope. Okay. If W changes from 0 to 1, then loss changes from 2 to 4, which is not much. But if B changes from 0 to 1, W changes a lot, because the slope of the graph is too much. Okay. So that means the graph has a steeper slope for the parameter, independent parameter B, than the independent parameter W. Okay. So this is the point where it will come to our help for calculating the gradient descent. So that means what? If I have a single two-dimensional graph, I can easily calculate the value of W, rate of change of loss with the respect to the value of W. Similarly, I can calculate the rate of change of loss with the value of B, with respect to the value of B. Okay. So this is where our partial derivatives comes into the picture. Partial derivative. Okay. You guys, anybody of you remember partial derivative, or I'll give a little bit of crash course. Okay. So this is my curve. This is my curve. Now I will bring this curve here. This is the same blue curve. Okay. This is my curve, and I want to calculate the partial derivative of this curve. What is partial derivative? If y is a function of x, sorry, if y is a function of a and b, and I am deriving, so partial derivative symbol is like this. If I am calculating the partial derivative of y with respect to only variable a, keeping b as fixed, This is called the partial derivative of y with respect to a, keeping b as fixed, plus the partial derivative of y with respect to b, keeping a as fixed. Okay. So we cannot calculate the derivative of a graph with respect to all the variables at the same time. If my equation is this linear equation, so it contains only a and b and w as variables, learnable parameters. But suppose I have a polynomial equation and I have 20 learnable parameters, then there is no way I can calculate the derivative of the of the loss curve with respect to all the 20 parameters at the same time. It is not possible mathematically. But what is possible? I will make all the 19 variables constant and calculate the partial derivative of one variable. Again, make other 19 variables constant, calculate the partial derivative of another variable, and so on. This I can do. Okay. So this is what they have done here. See, partial derivative of MSE. What is MSE? MSE is the loss, right? Partial derivative of MSE with respect to B, partial derivative of MSE with respect to W, right? And this is called the chain rule. This is called the chain rule. How we can partially calculate the derivatives of the loss with respect to variables and then combine them together to get the total derivative. Okay, this is called the chain rule. So, but don't be scared. We don't have to mathematically solve all the partial derivatives. There are direct formulas, direct library function calls which will calculate the partial derivatives for us. But for your understanding, the first chapter, we are learning that what is actually done behind the hood. Okay. So I'm not going into the formula in depth for partial derivatives. If you want, you can study this as a separate chapter in calculus. It will tell you how partial derivatives are calculated. So our function is MSE, and I'm calculating the partial derivative with respect to B. Here, W is constant. Here MSE, I'm taking the partial derivative with respect to W. Here B is constant. And after calculating the partial derivatives, this is the formula. This is the formula. Okay. You see here, the gradient of B, that means partial derivative of B is equal to 2 into error mean. 2 into error mean. 2 into 1 by n, this is what? Error mean, right? So the partial derivative of loss with respect to B, keeping weight as W as constant, is 2 into mean of error. That's why here we have done this. So that means what we did, by hand we calculated the partial derivative and then we coded. By hand we calculated the partial derivative and then we just plugged in that formula here. And similarly, the partial derivative of W of loss with respect to W keeping B constant is 2 into xi training data multiplied by error divided by n. Training data into error mean, right? So by hand I calculated this mathematical formula and I just plugged in the formula here. Okay, so now let us do this also in our code. So here now we had calculated the loss. Now our second step is to calculate the gradients, right? So we have to calculate the gradient B gradient, W gradient. Okay. We calculated the partial derivative of B, partial derivative of W. And loss, right? Squared errors. No, this is plus. Okay. So what we did, we randomly, this one will be outside the for loop. Sorry, this is first time we will and randomly assign. So we randomly took B and W. We calculated the y hat value, got the error, calculate the loss. Using the loss, we calculate the partial derivatives of the two learnable parameters, that is B and W. Now who can say what is next? We got the gradients, but what is next step?
We have to assign this B and W is equal to B gradient W gradient.
So we have to get the new value of B and W, right? I have to get the new value of B and W. How do I get the new value of B and W? This is the way.
Is that we will subtract the gradient from the original?
Yes. New B is equal to old B minus learning rate into gradient of B. New W is old W minus learning rate into gradient of W. And here you can keep learning rate is equal to say 0.1. So this is our, what is this step called in machine learning, deep learning?
Back propagation.
Yes, this is the back propagation step. Okay, so that means if B's gradient is steeper, then B will reach the minima faster than W, right? If W's gradient is steeper than B, then W will reach the minima faster than B. So our total loss calculation or our gradient descent will be dominated by the variable having the steeper curve. Our total gradient descent calculation will be dominated by the variable having the more steeper curve. So this is complete machine learning. Okay, this is complete machine learning or deep learning, you can also say, using NumPy. Okay, this is what happens actually behind the scene. Okay. Now what will happen every time? I'll show you here. Okay. So visualizing the gradients, you can also visualize the gradients. Okay. So this is keeping B fixed. This is the gradient of W. Keeping W fixed, this is the gradient of B. So B is more steeper and W is less steeper. So B will reach to the minima faster than W. Okay. This is also one, is just showing it, how the calculation is done. Now, whatever you said that this is the back propagation, it is described here. The back propagation algorithm works by computing the gradient of loss function with respect to each weight by the chain rule. computing the gradient one layer at a time, iterating backward from the last layer to avoid redundant calculations of intermediate layers of chain. Now one thing you have to remember here, that I have shown you linear regression. Linear regression is actually a single layer deep neural network, right? Can linear regression be thought of as a single layer deep neural network with linear activation function?
Yes.
Yes, yes.
So with respect to a single layer, I am doing this. This is my approach. This is my approach for a single layer. But if I had two layers like this, suppose I had two linear equations, then what I will do, this one will become B1 W1. From B1 W1, I will calculate B2 W2, and I will get B2 W2. So chain rule. That means calculate the gradients from the loss. Using that gradient, update the last layers B and W. Using the last layers B and W, calculate the gradient and update the penultimate layers B and W, and so on. Right? Here we have only one layer, so we are only doing this one time. But if we had a multiple linear layer, I will also show that example also, where I have multiple linear layer of linear regressions attached to as a pipeline to attach to each other. So there you will see that this back propagation is happening twice, okay, for each layer. And this happening of back propagation per layer is called chain rule, the chain rule. Okay, this is how it happens. Okay. Next is what? Next is learning rate. Okay, so learning rate is the most important hyperparameter. We already know about this, right? Learning rate is the most important. There is a lot of material on learning rate to be learned about. Okay, and how to choose a learning rate which is too big, which is too small, which is perfect for your model. So there is a lot of maths behind it. So I'm not going to go through that, but I'm just telling you in general is that if your learning rate if your learning rate is too big, then what will happen? From this step you will jump here, you will jump here, and you will jump here, right? If the learning rate is too big, then what is happening? This is the minima, suppose. Okay, so you will have two big learning steps. So you will jump across the minima and reach the other side. Then from here again you will jump to this side. Then from here to jump this side. So what will happen? You will keep jumping across the minima point multiple times until you converge. Right? So this is the demerit of having a bigger learning rate. And what is the demerit of having a smaller learning rate? You will ultimately reach the minima, but what will happen? You will reach very slowly. You will reach to the minima very slowly. So that is the difference between having a bigger learning rate and a smaller learning rate.
Hello, I had a doubt, like if that's the case, then can't we do the dynamic learning rate, like
Yes.
when it is far it do big jumps and when it is close it do small
Yes,
jumps?
exactly. There is a learning rate for that optimizer called ADAGRAD.
Okay.
Adaptive gradient descent.
Okay, so that's a learning rate function, no?
Yes. Yes.
Okay.
We have different learning rates for different parts of the gradient descent curve.
Okay.
So this is our learning rate now. We have done big learning rate. I said you problem. Small learning rate. I said you the problem. And now What's more? Now we will talk about one more thing that is not directly related to what I said, but it is important, called scaling, standardizing or normalizing. Okay, scaling, standardizing or normalizing. Um, Let me share the screen. Scaling, standardizing or normalizing. Okay, we all know about this function standard scaler, right? We use it very often, but we really don't know what it actually means. Okay, it transforms a feature in such a way that it ends up with zero mean and unit standard deviation. Okay, so you guys are clear on statistical this mean standard deviation, right? Any confusion in there?
No.
Okay.
No, sir.
So that means I might have a very big range of values, starting from 0, minimum is say 10, maximum is say 20 million. But if I put that data in the standard scalar standardizer for function, then what will happen? It will standardize it so that it has a mean of 0 and a standard deviation of 1, whatever be my original data's distribution. Okay, it will make it which type of distribution has a mean of 0 and standard deviation as 1? Can anybody say?
Normal distribution.
Gaussian distribution.
Okay.
So that means any distribution will be converted to a Gaussian distribution using this function. Okay, there is the formula here. 0 mean and unit standard deviation. It is told here. It is given very important. Principal component analysis is also helpful. Vanishing gradient problem. All this will come to picture here. We'll talk about this. Not now. Okay. So standard scalar with mean with standard deviation. You have to that fit the training data there. So it transforms the data to scaled data X value, scaled Y value, X training data and validation data. Okay. Now, why it is done is that because if you see the slope, okay, here you see original slope, how it was. Okay. The loss surfaces for different scales of features. Left and center plots look a bit different than figure 014 because they're centered at the scaled minimum. So you see here, this one is scaled one, okay, and this is bad. See here, the steepness of the curve is very high this side, and it is not that high this side. So what happens is that the data is not uniformly distributed. When the data is not uniformly distributed, then gradient descent doesn't happen properly. And it takes a lot of time for gradient descent to happen. So that's why it is very important that we scale our data to a standard scalar of 0 mean and unit standard deviation. Then you see the data is so nicely distributed here. You guys are able to understand contour plots, right? So every line, it is written here 2500. That means the height of this, all the data points in this circle is 2500. This data point is 3000. This data point is 3500. So that means you see it is evenly spaced, 500, 500, 500, 500. Like this it is spaced. So the data is very uniformly spaced. So what will happen, the beauty is that our gradient descent will happen very uniformly and it will reach the minima very nicely in a very optimum time. But if the data is like this, here you see it is not a circular data, it is a flat data, and it is 80,000, it is 1,60,000. So the gradient steepness is very high here. the steepness is not very high here. So what happens is that this curve is skewed curve. One part is very steep, one part is flat. So gradient descent doesn't happen properly here. And it sometimes takes a lot of time to converge. Okay, so that is why this one is very important. Scalar, standard scalar. We should always take our training data and validation data and scale it to zero mean and unit standard deviation, and then apply to our model for learning. So this is always keep in mind. This one will be helpful. Okay, here it is one example it is given here. Think of two common features in a model: age and salary. While age usually varies from between 0 to 110, means a person can be minimum 0 age and a maximum 110 age. Salaries can go from the low hundreds, say 500, to several thousand, 9,000. Okay, if we compute the corresponding standard deviations, we may get values like 25 and 2000 respectively. That means for age, the standard deviation is 25, whereas the salary, the standard deviation is 2000. Okay, thus we need to standardize both features to have an equal footing. Okay, so you see here, this one is much steeper standard deviation, and this is very flat standard deviation. So if I am computing gradient descent and these are my variables, then it is this the rate of change with little bit of salary, the rate of change of loss is much more than the rate of change of age. So that is a problem, right? So we have to make all of them equally spaced, equal standard deviation from the mean, so that we give them equal opportunity. Okay, zero mean, that is centering the feature at zero. Deeper neural networks may suffer from a very serious condition called vanishing gradients. Since gradients are used to update the parameters smaller and smaller, that is vanishing gradients means smaller and smaller updates up to the point it stands. The network simply stops learning. One way to help the figure network to fight this condition to center it inputs the features at zero. Okay, this is one of the benefit of centering the input of a data at zero. It will help in avoiding the vanishing gradient problem. Okay, so this is our one of the use case. Okay, what's more?
So this way, centering the inputs means the standardizing, right?
Standardize, make mean as zero, standard deviation as 1. Okay, so now you understand here one point. Who can tell me what is happening here? Gradient descent, stochastic gradient descent, or batch gradient descent?
I think it's stochastic.
Dennis?
The PDF only is visible.
Oh, sorry. Yeah.
Okay, so in this, I think there is batch gradient descent.
Vivek?
Yeah, I think stochastic.
Okay. Here, to calculate the gradient of B, what are the learnable parameters here? B and W?
Yes.
To calculate the gradient of B and W, we are using loss, right? To calculate the loss, we are using all the values of Y and X. Is it not?
Yes.
Am I taking a batch of X value?
No,
I am taking all the values of X to calculate all the values of Y and calculate all the values of others.
Yes.
So this is gradient descent.
Fully.
But here, if I would have put one more loop here, huh? and in that loop I would have taken a small batch from x underscore trend, then it would have been batch gradient descent.
Okay.
And if I would have taken one item from x equal to trend, like xt in x trend, like this, then it is stochastic gradient descent because I'm taking one values. Okay. So this is stochastic gradient descent. This is batch gradient descent. Got it?
Right.
Yep, got it.
This is very important. Always keep in mind. Okay, because slowly we will, because I will show you why gradient descent, normal gradient descent is not possible, because you cannot calculate to calculate this gradient, you have to calculate this loss. To calculate this loss, you have to calculate the error of all the data. That means you have to load everything into memory to calculate, right? So graphics card memory unit, graphics card maximum will be 4 GB, 5 GB, 16 GB. But we can have records of millions of records. We cannot calculate that way, right? So how to do that? So that's why you need batch gradient descent. Okay. So that one mostly we use batch gradient descent, and how to choose a batch size also is very important. That will also help you in making faster gradient descents. Okay, so that is also important. What else is remaining? This is important. So this is how gradient descent happens. You see, if you take batch gradient descent, then this is the minima. Okay, this is the minima, and you started at random start point. This one, this is your random start point. This is your path. This is the path you take to reach the minima. This is batch gradient descent. Okay, this is mini batch gradient descent. Means first batch, then that batch is mini batch. Okay, so this is the mini batch gradient descent, and this is stochastic gradient descent. You see, stochastic gradient descent is the fastest, but it may miss the minima point. See, it missed the minima point. It went out away from the minima point. Okay, so this is the three differences here. You will understand nicely. Okay, so batch 80 data points, one update epoch totaling 100 updates, 16 data points mini batch, 5 updates totaling 500 updates, and one day. So okay, let me ask this one here. If I am doing a gradient descent, then how many a number of epochs is 100, then how many updates will happen to the learnable parameters?
It's gonna count.
100.
How much?
100 updates. Like
Yes. If I am using a batch of 10, then how many updates will happen to my learnable parameters?
10.
1,000.
Yes. For every batch, there will be 10, and 10 such batches are there. First,
like, I had a doubt. Like, how can we say that if there are 50 data points, then for 10 batches, we will be having 5 data points per batch. So every batch will have 5 updates, right?
Yes, sir, definitely. It will divide it by 10, not multiplied by 10.
just a minute, just a minute.
Also, we can see the difference. The stochastic gradient descent will have a 100. Hello.
Yeah, I'm here. So
Yeah.
the
So
what is
it will have 100, and if we are using the batch, it will definitely give a lower updates, right, compared to the
okay? This is
basic one.
important here. This one I think we need to see here. This definition. What is the definition of an epoch? Okay, an epoch is complete whenever every point in the training data set has already been used in all steps: forward pass, computing loss, computing gradients, and updating parameters. So in one epoch, I will tell that one epoch is completed only when all my data points in the training set are used. So if I am using a normal gradient descent, then what will happen? All my data points will be used in the single epoch only, correct?
Right.
So my all training set are used for in the single. So my one single update is equal to one single epoch. If I'm using a stochastic gradient descent, then per data point there is one update.
Right.
Yes.
Then one epoch is n data points,
Yes. Yes.
and there are total n times, means n epochs are there. So n into n square updates.
Yes.
Similarly, batch gradient descent is so suppose per batch I am making 5 updates. I am using 5 training data to calculate the loss and calculate the gradient and updating the gradient. And I have total 100 training data. So what will happen? I will do it 20 times.
Yes.
After doing 20 times, only I will say that one epoch is completed.
Yes.
And I have to do total 100 epochs. So 20 into 100, 2000 epochs, so 2000 updates will happen total.
Right.
So this calculation will help you in understanding how quickly your model will converge. Okay, the number of learnable parameters and the total number of, because the total number of update means that many time IO operations are happening in the GPU, and every IO operation is costly. So that is the way you can, so suppose you have to deploy a model in a semi-embedded platform, then you can do these calculations and then apply there. Okay, because so Raspberry Pi, edge computing device, so these type of devices are very low in memory and computing speed. So we have to design a model such that minimum number of updates happen. Okay, so this is one thing here. Okay, what else? That's it. Yeah. So I think that's it. So this is our NumPy deep learning with a single layer, which is also called linear regression. Okay, so this is if you imagine a neuron is there, in a neuron X is coming, its weight is this one, activation B, and error is epsilon, and output is Y. So this is a single layer neuron. What is the name of such a neuron called? Perceptron. Okay, the most basic kind of neural network. Okay, and to update such a neural network, this is the code. This much is the data generation part. Sorry, this one also. This one is the data generation part, and this one is your gradient descent. Okay, this is how you are learning. Okay, now next chapter we will see how we can use PyTorch and achieve the same thing only in 3-4 lines of code. Okay, and then slowly we will increase the complexity of coding. This is very simple code. Slowly we will increase the complexity. So who can say if there are 2 layers of there were 2 so suppose this equation's output was here, like z is equal to 2b2 plus 2w2 into y plus epsilon 2. If this was the equation, you have to find z from x. Then what change we have to do here?
We will add another loop inside the y for z.
No, it will in the same only. How many learnable parameters will be there now? You tell me.
4.
4.
Hmm?
1 parameter, 2
Yeah.
parameter, 3
That's right.
parameter, 4 parameter.
Now we have to add D2 and W2 variables.
So this is the first layer. This is the second layer. The loss generated at the end will be used to update the B parameter and W parameter here. The Y's value generated here will be used to update the B parameter, W parameter here. Got it? So I'll do a diagram and show you. Okay, so y is equal to b plus w x plus epsilon. Let's say b1 w1 epsilon 1. Z is equal to b2 plus w2 y plus epsilon 2. Okay, so this is my equation. Now if I have to draw neural network, how it will be? This is x is coming here. Okay, y is going out. Correct? This one is w1 and epsilon 1 is coming. B1 is coming. Y is coming in with weight W2. Epsilon 2 is coming here. Base value 2 is coming here. And this is Z. Right? This will be the neural network, isn't it?
Yes, sir.
So if I have to, so my learnable parameters are W2, B2, W1, B1, right? So here I will calculate the loss. Using this loss value, I will update W2, B2. So loss will be generated here. So partial derivative of loss with respect to W2. Similarly, partial derivative of loss with respect to B2. This will help me calculate my new value of W2 and B2. Similarly, the value of Y here will help me calculate the partial derivative for W1 and B1, and so on. This is called the chain rule. First apply for this layer, then apply for this layer, and keep on going. Right? This is a single node multi-layer neural network. Right? I can chain as many linear equations I can, right? I can put here F is equal to B3 plus W3 Z plus epsilon 3. So it will again connect here one more, right? Getting the point, or any doubts?
So you meant to say, Vishwa, like every neuron in a deep neural network is a linear equation of values.
Yeah, if you have no activation function. If I have no activation function in this neuron, okay, then what is it basically?
Linear.
W1 into X plus epsilon into B1 is equal to Y. This neuron is the summation. What is coming? X is coming. W1 is the weight of this edge. Epsilon is the error 1. B1 is the bias. This is Y. Y is equal to B1 into X1, B1 plus W1 into X plus epsilon 1 is equal to Y. Now, if I remove this here and put some activation function like sigma, then what will happen? Y is equal to, it will be no more a linear function. It will be a function of sigma. It will be B1 plus W1X plus epsilon. Got it?
Yes, yeah.
So now this is no more a linear function. But if I remove the sigma, it becomes a linear function. So whenever there is no activation function in a neuron, it is called a linear function. But if we have a activation function which is not linear in nature, like tanh, softmax, ReLU, sigmoid, then it is called a nonlinear activation function. Okay.
Okay.
So as a homework, what I want is that
This way, one more doubt, like in real time, how we decide the epochs? Because if we are using more epochs, then it can miss our minima, right?
Tell me again, I didn't get your question.
So how, in real time, how we are deciding the epochs, like 100 or 1000? Because if we are using more epochs, then it could miss our minima point, right?
No, see, the epoch is you get a so there is some concept called a early callback. Okay, so that means early callback is if you have say 10,000 epochs, but after say 5,000 epochs, the gradient value is almost zero, not changing. Okay, so if the gradient value is not changing, almost zero, then there is nothing to learn for the learnable parameters, is it not?
Yes.
Learnable parameters is what? New value is equal to old value minus learning rate into gradient. If gradient is zero, then old value is new value.
Correct.
So if I see that after, I will keep a limit, say after 20 epochs also, if I see my gradient value is remaining as zero only, then I will break the learning. I will break the epoch there, even though I have 5,000 epochs more remaining.
Yeah, got it.
So there are many policies you can apply in your deep learning technique in which you can tell that early stopping you can do. This is called early stopping. One is you achieve the desired accuracy. Another is that I said the gradients are not changing. So many policies are there. You can apply those policies and you can do a early stop. It is not necessary that it will always has to complete the number of epochs that you gave. Okay.
Yeah. Yes. Got it.
Okay. So as a homework, what I want you guys to do is, I want this one. This is your um, system of linear equation. Okay. I want you guys to write the code in NumPy for training this system of linear equations. I showed you example of 1. You have to do the same extent for 2. Okay, where this y will just come in here. Okay.
Okay.
Okay, sir.
Divi, Vivek.
Okay, sir.
Yes, got it.
Okay, let's meet tomorrow then, and I will see you.
I have one doubt.
Tell me.
This back propagation, this always means start computing from the backward means from the low, right?
Yes, from the
Or
end,
or
last
it will
part.
update. Okay, so it will update parallelly with each chip means at each update.
Sorry, I'm not getting, your voice is very low.
Yes, I am saying that at each update, this both parallelly the process of back propagation and forward pass. This all goes parallel at every update.
No, it goes by chain rule. So you have to study the chain rule.
Oh, okay.
How is chain rule applied? How I can propagate the loss across multiple layers. So do some R&D on chain rule in YouTube, and then you will be able to solve this.
Okay.
Okay. Okay, let's meet at 2 o'clock then tomorrow.
This way, one more thing. Like, since I'm not I'm not from the programming background, so like you do in real-time projects, like all the skeletons, like classes and constructors creating. So if we can also implement the same way.
Yeah, we'll do it. We'll do complete class object-oriented programming. We'll do. Now it is just beginning. That's why I'm showing you full basic.
Okay.
If I use library, then what is the point? Many things you already know those things, right? So
Yeah.
something, if I write something dot train, now what is happening inside that train, you don't know, right? That is why you are coming to this class, right?
Yeah.
So that is the main target. So if we understand the fundamentals, then we can design models which are perfect for our use. Now what we are doing, we are copy pasting from somebody wrote it, we are just copy pasting it, and it is working. So by luck, by chance, it is working, and we are smart enough to adjust it somewhere, cut and paste we are doing, and it is happening, working. But that is not the way it should be, right? We should understand every line of code. Why is it written there?
Yeah. Yes.
Okay, guys. Okay, so let's meet tomorrow at 2 o'clock. Then, thank you.